I am Anirudh, and in this video, I shall give a brief review of the paper Ultrafast Photoelectron Transfer in Bimetallic Porphyrin Optoelectrode for Single Neuromodulation. The presentation is split into 5 sections as follows. In the first section, I shall briefly describe the introduction and motivation behind this paper. In the second section, we shall look at the photophysical processes that are involved in the design of this nanoelectrode. In the third section, we shall look at the electrode-electrolyte interface. And in the fourth section, we shall look at the comparison between this architecture and several other architectures and topologies that have been presented in previous literature. And in the final section, we shall look at the highlights of this over other papers. Now, moving forward, the motivation for this article is the need of precise neuromodulation. So, neuromodulation is a procedure that uses electrical or chemical stimulation to change the activity of nervous system. And as we are shrinking the size of optoelectrodes, we can ensure that precise neuromodulation of a single neuron can be achieved. However, conventional photovoltaics, which have been used for neuromodulation till recently, result in reduced efficiency as a consequence of the Gauss-Chapman theory. And the highlight of this paper is that this presents a nanoelectrode design that can efficiently inject up to 4 picocoulomb of charge within millisecond laser pulses. And the theoretical threshold for deep brain neuromodulation is about 3 picocoulomb, and this injected charge 4 picocoulomb being greater than the threshold of 3 picocoulomb is suitable for deep brain neuromodulation. That is the motivation behind this paper. Moving forward, we shall now look at the photophysical processes that are involved, starting from the material choice to the charge generation mechanism. The most critical aspect is the choice of material, and the material used here is zinc gold porphyrin. Porphyrin based optoelectrodes have been known to have robust abilities in light harvesting and fast energy conversion, and it has also been seen that P and N conduction can be modulated by doping of transition D metals in these porphyrin based materials. And there is an observation that zinc porphyrin and gold porphyrin, when held in an oblique orientation, result in an extremely high quantum efficiency of about 97%. This is the structure of zinc porphyrin and gold porphyrin held in an oblique orientation that result in this 97% quantum efficiency, which we shall see later. And this is the structure of this zinc gold porphyrin interfaced with neuronal cells, as we shall look at in much greater detail later. The charge generation and separation in this structure is as follows. The first step involves the photoexcitation of electrons. That is, light is incident on this material, and the electrons in the ground state are excited to a higher state because of the energy of this light. This excitation can be done using two methods, that is, using a single visible photon or using a near infrared 2 photons. And there are two possible routes for this electron to come back from this excited state to the ground state. That the first possible route is the intramolecular charge transfer, which takes about 2.7 picoseconds, as I shall show in the next slide. The second route involves an energy transfer between zinc porphyrin and gold porphyrin, plus and a charge transfer from this gold porphyrin to uncoordinated gold atoms in 66 picoseconds plus 0.5 picoseconds. And the efficiency of this combined system is about 97%. And this earlier, as we saw, is excitation from zinc porphyrin to its excited singlet state using either a single photon or two near infrared photons. And this excited electron can either move directly via charge transfer from this excited ZnP to this AUP in 2.7 picoseconds. This is the intramolecular charge transfer route. Or it can move via this energy transfer to AUP plus and a charge transfer from AUP plus to AUP in 0.5 picoseconds. And the molecular dynamics has been described here as well. The charge transfer from zinc to gold can happen in 2.7 picoseconds or via this energy transfer plus charge transfer route. The mechanism in conventional photovoltaics is slightly different. It involves the generation and dissociation of exciton. An exciton is a bound electron hole pair. The first step in a conventional photovoltaic is the generation of an exciton. The second step is the diffusion of an exciton. The third step is dissociation. The fourth step is carrier collection. So light is incident on this material, and this results in a bound electron hole pair formation, which is termed an exciton. And this exciton then diffuses to the interface, where it then dissociates to give rise to current, as we see here. The same thing has been described here. The first step with other possibilities. The first step involves incident of light. The second step involves the formation of exciton. Then the next step is the transport of exciton. And in presence of excess energy, which could be possibly field or temperature, the exciton gets dissociated, giving rise to a photovoltaic current. Or it could lead to the exciton recombining, giving radiative decay named photoluminescence, or non-radiative decay, which results in the same state as before. And in comparison to zinc porphyrin, which was used earlier as optoelectric material, the advantages of zinc gold porphyrin is that AUP, gold porphyrin, is non-fluorescence, which results in a reduction in lifetime of singlet excited zinc porphyrin. So as a consequence of this lifetime reduction of zinc porphyrin, here the lifetime of this is reduced. As a consequence of that, this intrinsic fluorescence of zinc porphyrin is quenched. That is not evident here in zinc gold porphyrin. And the intersystem crossing is suppressed in zinc gold porphyrin due to the introduction of gold. And due to the heavy atom effect of gold, the electron is transferred from AU porphyrin to single atom gold centers in 500 femtoseconds, which is an ultra fast electron transfer mechanism. That is the highlight of this paper. As we can see, the time delay is significantly reduced, and it has observed that an optimal zinc to gold ratio of 1:1 yields a maximum photocurrent of up to 10 nanoampere under an excitation of 59.24 milliwatt per centimeter square laser of 670 nanometer wavelength and 10 milliseconds time period. And this zinc gold porphyrin has these metal ligand interactions, which result in the pi cloud electron extension along the porphyrin ring, as a result of which the homolumo gap of zinc gold porphyrin is reduced. As you can see, zinc porphyrin has homolumo gap of 5.67, gold porphyrin has 5.84, zinc gold porphyrin is only of 3.79. This results in faster transition, and as we saw previously, the intersystem crossing is prevented. This is the intersystem crossing in zinc porphyrin, which is prevented in zinc gold porphyrin. This is the mechanism in zinc and gold porphyrin, that is the substrate we use here. So there is an energy transfer between zinc porphyrin to gold porphyrin plus, which is then electron is transferred from zinc gold porphyrin plus to AuP. That is the second route, as we saw earlier, which takes about 66 picoseconds. The first route, as we saw earlier, is the charge transfer directly from zinc porphyrin to gold porphyrin, which takes about 2.7 picoseconds. And the charge transfer between gold porphyrin plus to gold porphyrin is only in about 0.5 picoseconds, which is 500 femtoseconds. And contrasting whatever we saw till now, the charge generation mechanism in zinc gold porphyrin can take place via energy transfer and charge transfer, whereas in a zinc porphyrin, it's only a charge transfer mechanism. And in a P3HT based material, it is only via the formation of exciton. The processes involved here are also slightly different. In zinc gold porphyrin and zinc porphyrin, the mechanism is Faradic mechanism. We shall see what Faradic mechanism is moving on. And in P3HT, the mechanism is a capacitive mechanism. The time scales involved are also drastically different. In zinc gold porphyrin, the time scale involved is only 70 picoseconds, whereas in zinc porphyrin, it is 1.9 nanoseconds. And in P3HT based, it's about 3 nanoseconds. The quantum efficiencies are also drastically different. In zinc gold porphyrin, the efficiency is about 97%, whereas in zinc porphyrin, it's only about 36%, whereas in P3HT based PVs, it's only up to 80%. The equivalent circuit can be viewed as follows. The incident photo energy, light energy, is converted into an equivalent current source, which drives this circuit. This diode basically represents the reverse leakage dark current of the photovoltaic under zero light excitation. This RSH represents the leakage losses in the photovoltaic system. This RS represents the contact resistance, and this RL is the effective load resistor of the neuron. And now we shall move on to the electrode-electrolyte interface. And before we move on to the electrode-electrolyte interface, as we saw earlier, there are two types of charge transfer mechanisms. The first being capacitive, the second being Faraday. The capacitive process involves the generation of two oppositely charged Helmholtz layers at the polymer and neuronal interface. And the Faraday process, on the other hand, involves reduction and oxidation reaction between species in solution and electrodes. And as you might have anticipated from the previous statement, there is no direct electron transfer in a capacitive process, whereas a physical electron transport occurs in a Faraday process. And in capacitive process, there is no chemical reaction. On the other hand, there is a physical reduction oxidation, which implies there is a chemical reaction involved in a Faraday process. And the typical characteristic of a Faraday process while measurement is that there is a constant current waveform that is obtained in steady state, which is not a characteristic of the capacitive process. And it is typically assumed that a Faraday process is much more efficient than a capacitive process. And this is a diagrammatic illustration of the same. There is induction of charge at the electrode-electrolyte interface in a capacitive process, whereas in a Faraday process, there is physical transport of electrons from the electrolyte to the electrode. And this is the gold-based arrays that is used in this paper. Due to the heavy atom effect of gold, the excited electron can be transferred from AUP to AU atom center at an ultra-fast relaxation of only about 0.5 picoseconds. Thereby, the electron-rich single AU electrodes are ready for robust charge injection at the zinc gold porphyrin and neuron interface. This is attributed to the heavy atom effect. The heavy atom effect is basically a complex way of saying the introduction of a heavy atom. Due to the introduction of a heavy atom, the probability of crossing from a singlet to a triplet state increases. This is termed intersystem crossing, and this is a consequence of spin or orbital interactions becoming large. And there are two main consequences of this effect in this paper. The first thing is that the introduction of gold quenches the intrinsic fluorescence of zinc porphyrin, as we saw earlier. The second effect is that there is an ultra-fast transfer of electron from AUP to AU atoms in about 0.5 picoseconds or 500 femtoseconds, which is a key characteristic of the heavy atom effect in this paper. And now we shall move on to the neuron electrode interface. So this is the diagram of a neuron resting on top of an electrode. The junction between a neuron and the electrode is typically termed a cleft, and this leads to the formation of a resistance that is typically referred to as a seal resistance. And this cleft is typically filled with ionic solution. And the voltage that is formed over this R seal is critical, as this directly modulates the gate voltage of a field effect transistor or the charge deposited over an electrode, and that's why it's of great concern to us. And the voltage that is generated by a neuron is typically distributed across two impedances in the neuron itself. The first one is a non-junctional resistance, that is the resistance and capacitance that is away from the sensing electrode, and the junctional resistance and capacitance, that is the one that faces the electrode. And obviously the electrode comes with its own parasitic resistances and capacitances. And since we want the drop across this R seal to be large, we require this R seal to be large. And typical values of R seal are of the order of 100 mega ohm, whereas this junctional resistance is of the order of giga ohms, and this non-junctional resistance is also of the order of a couple of 100 mega ohms. So that concludes the part on electrode-electrolyte interface. Now we shall look at comparison across material, architectures and topologies that have been presented in previous literature. The first structure which we shall look at is a silicon-based PIN nanowire that was used for dorsal root ganglion excitation. The laser used here is a 532 nanometer laser with a power of 17 milliwatt, and the period of this laser was about 10 milliseconds. The process involved here was a Faraday process, and the peak current that was reported in this case was 101 picoampere. not the most efficient, as we shall see. And the second and third basically involve organic photovoltaic materials, that is mainly P3HT. The first organic blend, which we shall see, is a P3HT PCBM blend that was used for hippocampal cell stimulation with a 532 nanometer laser and an intensity of 10 milliwatt per millimeter squared. And the time period of the laser was 10 milliseconds. The process that took place here was dominated by a capacitive process, and the peak current was 1 nanoampere. The next is a P3HT PEDOT PSS blend that was used for renal prosthesis. The laser used here is typically of the same order, 530 nanometer. However, the intensity and time period of the laser are drastically large. The intensity of the laser is 200 milliwatt per millimeter square, whereas the laser time period is also 10 times larger, that is 10 milliseconds. The process is still the same, it's a capacitive process, and the peak voltage reported is about 100 microvolt. Then we move on to another paper published by the same group that involves a zinc porphyrin plus TiO2 nanorods that were used for cortical neuron stimulation with a 532 nanometer laser. The intensity of the laser used here was 13.5 milliwatt per centimeter square with a time period of 2 milliseconds. The process involved here is non-faradic, and the peak current reported here is 18 picoampere. In my literature survey, the power consumed by this structure is the least. However, the peak current generated is much lower compared to this paper, as we shall see. And another structure is TiO2 doped with gold nanowires that was also used for retinal cell stimulation. This structure was excited using 3 different lasers that correspond to RGB, 375, 470, and 546 nanometer, with an average intensity of 470 microwatt per millimeter square. The process here is a combination of faradic and capacitive process, leading to a peak current of approximately 800 picoampere. Another non-efficient way of retinal neuron stimulation is using P3HT nanoparticles that involves a 540 nanometer laser with an intensity of 400 milliwatt per millimeter square and the time period of the laser being 500 milliseconds. The process here also is capacitive, and the peak current reported is of the order of hundreds of picoampere. Now we move on to some non-conventional excitation methods. The first one is indium phosphorus zinc sulfide quantum funnels that were used for neural cell stimulation with 450 nanometer laser with an intensity of 169 milliwatt per centimeter square and time period of laser being 100 milliseconds. And the faradic process was attributed for current generation here, and the peak current was about 250 picoampere. And another possible structure that was used for neural cell stimulation is aluminum antimony based nanocrystals. They also were excited with typically about the same wavelength, 445 nanometer, and an intensity of 100 milliwatt per centimeter square and the time period being 20 milliseconds. The peak charge reported was 0.19 microcoulomb per centimeter square, and it was attributed to a capacitive process. And this is the final highlight, zinc gold porphyrin that was used for motor neuron regulation. And as we saw earlier, any visible light or near infrared light between 400 and 700 nanometer does the job. And the intensity of the laser typically used for measurement was 17.4 milliwatt per centimeter square, the time period of the laser being 5 milliseconds. Though this ranks just after this, the peak current in zinc gold porphyrin is substantially higher, that is 1.1 nanoampere compared to the 18 picoampere reported here. And the process involved here is a faradic process. And all the references have been cited here, which can be clicked and viewed. And now this brings to the conclusion of this paper. This paper successfully demonstrates the design of zinc gold porphyrin based nanoelectrodes, which give an efficiency of up to 97%. Precise spatial and temporal resolution can be obtained using millisecond laser pulses. And the key highlights of this design include high charge per pulse energy, low energy per pulse to attain action potential, and light used can vary from visible to near infrared. And this method is suitable for deep brain stimulation, as we saw earlier. Thank you.